Here. Okay, so the recording is getting started, is on right now. So thank you for everybody agreeing to let me do that. All right, so we're going to start with lab number 1. Let me go ahead and bring lab number 1 up so we can start with it. I went ahead and basically copied the code that was in lab 1 into here. Okay. And what I wanted to do is just go through it line by line and explain what each one of these lines is doing. And please feel free to jump in and ask questions if I'm saying something that doesn't make sense, okay? And as I'm going through this, I might go ahead and write some comments as well as an example of where you put comments, because your codes are expected from here forward to have comments on them as well. So if you look at this thing, the very first thing it says the processor type. Throughout this course, that will not change because we're going to be using PIC18F1220, right? And then this one basically says whenever I put a number down, unless I specify something else, it's always going to be hex. So in this language, you can represent this. So you can represent a number, and I'm going to erase this. So for example, if you have a number, let's say 16, and you want the 16 to be fourth decimal, you put a dot in front of it. Okay. If you want it to be hexed, I prefer to use 0x, which is like a which is the C-like indication that it's a hex value. Or you can also do this for hexadecimal. You can also do this. Okay. Now, because I have this radix hex here, I'm basically saying, look, whenever I just write a number 6, that's in hex. Whether I tell you it's hex or not doesn't matter. My default base is hex. So when I write a number, you assume it's hex. You can change it to DEC for decimal if you want. But in computer science and computer engineering, we kind of like hex. Because hex, unless you're dealing with a human, whenever you're in the computer engineering side of things, dealing with the processor and a lower level of your system, you like hex. Whenever you're dealing with the human, you like to have decimal. That's just how it works. And then the next thing is these things, and these are defines. They're just like the way defines were in C, right? In C, all they do is wherever in my code now I say port A, they just simply gonna put this number in. It's a way for me not have to put numbers in. Why do we do that? Because humans with numbers have a little bit of a problem. They can't remember the numbers as well as names. We remember names much better than numbers. So this is a way of giving a number a name. So whenever you want that number, you just give it the name. So for me, it's a lot easier to remember port A and port B. And later on, we find out why port A and port B, the names that are more important. But at this point, it's a computer assumes it's a constant. Everybody okay with that? Any questions?
Quick question is, so if our radix is hex, right? Then when we add the OX prefix to the numbers or the H afterwards, is that just like a courtesy to other people that would be reading our code later? Yeah. Just so that, okay, all right. I just wanted to, yeah.
Actually, that's a great point, Tim. I think it's more than, we are helping them. We are helping the human reader to know what number we are doing explicitly.
Right.
But the other point you're making, I think implicitly, is that we don't have to do it.
Right. That's what I was checking. So yeah, we don't necessarily, the computer will understand what we're talking about if we leave the OX out, right? But we're doing it for the human reader. Yeah. So
you're exactly correct on that.
Okay.
So the next thing is this thing, this config file. I jumped over it, but this config file, all it's saying is that it's configuring the processor the way we want to do it. And I'll say what they are, but I don't want to spend a lot of time. Otherwise, this lecture gets really long to go through it. We're going to have plenty of time in chapter 4 to come back and talk about these. This basically says a watchdog timer. And that basically is most computers have this heartbeat that you as a programmer or operating system or a BIOS every so often has to go and change the value in this register. That is telling the processor that the program is still running correctly and hasn't lost its way to crazy land. So if your watchdog timer is on and you don't do that, for us is every 100 millisecond. If you don't write to this register every 100 millisecond, it's gonna reset you. So you don't want to, so this is a safety feature in computers. I've turned it off because we don't want to get bothered by having to go someplace and write it, and we're not doing anything critical. So if it's lost, it's lost. Life will recover. This is a program, a low-level program. This is important. This way you can electrically program your chip over and over again. And then this one is a setting which says run, I don't remember what it says, but it says, I think we're running, it's saying that the RA6 as a, no, that comment is inaccurate, but this, I think we're running it at 4 megahertz. We're gonna run this clock at, I'm sorry, the clock is gonna run at 4 megahertz. We'll come back and deal with this. This is just assume these are some configuration files you have to do every time as we move forward. And then the other thing that's important, which is a configuration file, is this org thing. And this is basically telling the assembler and the linker, specifically the linker, and that when you create the assembly code for this, okay, start putting it in location 0. You started at location 0. So if you want your code to be put in memory at a different location, you just put a different number in here. So let me show you kind of what that means. So remember in when you do your labs, you got to turn in your disassemble code. And I think that disassemble code, if I remember where it is in, what was it? Window debug, right? Debugging, output, disassemble, that's where you get it from. Oh, and you remember how you fix that, right? If you get this thing, you go to your project. Oops. You go to your project, properties, and there's a loading here. You say, yep. Oh, it's already set. How come? All right. So we say, okay. And then if I come and there it is. Now, if you look at it, notice none of these generated any assembly, machine code or assembly code. You see that? Because this code gives you the assembly code you wrote, plus the way the assembly code was read by the computer, plus the machine code, plus where it puts it. Any questions? I'm kind of running through this rather quickly, so if you have questions, great. I would love to hear them just to make sure everything we needed to cover is being covered. So this piece is the address. This piece is the machine code. This is the zeros and ones that the computer sees that is equivalent to the assembly code you put in there. And this is the assembly code. How are we doing so far? Do you remember what port A is? It's F80. You see that? Okay. And so basically 80 tells you that's where you're putting it. And 6A somehow is telling the computer this command is clearf. We don't still know what clearf is, but then you gotta have an idea of what it's saying. I'm introducing a lot of new ideas. I just want to make sure you're with me. If something doesn't make sense, just bring it up. Now, having said that, I'm going to leave this. Now we're going to have to understand what the code is. So I'm going to leave the code from Lab 1, and we're going to go back to this summary sheet we talked about a little earlier. Anybody not able to find the summary sheet? Just if you raise your hand, I put a link in the chat if you want to click on it, or you can go to Canvas page and find it as well. Either one is fine. Either way you get there. All right. So let me go ahead and now that we kind of know what the beginning of the programming is, let's start to learn what the processor typically holds. And once again, as you're going through quizzes and the videos of the lecture, you're getting a lot more in-depth than what I'm going to cover here. What I'm trying to do here is just get you bootstrapped so you know how to write the program for the next assignments or next step to get you started. All right, so let's go ahead and clear everything. Okay, so this chip has 18 pins. If you got it in real life, it's 18 pin. It comes in different varieties. It comes either as a surface mount or a dip or whatever. But for now, we're not going to build with it. So the package we have looks like this. And if you notice, one of the things hopefully you've noticed is that this chip has a single pin has many values. And let me see if I can get some stuff. So single pin, for example, pin 1 can be either RA0 or AN0. You see that? And for example, if you look at some pin can be lots of different things. Look at this one. It can be something called RA0, something PGC, sometimes T1 OSO, sometimes is some sort of a clock, sometimes is another thing, and on and on. So this thing can be 1, 2, 3, 4, 5, 6 different things. So how does it know what it needs to be? Well, they have this register they call special function registers. There's a bunch of location inside the chip, memory location, literally, okay? And these memory locations start from, I think, F8, I'm sorry, for us, let's F00 and go all the way to FF. I'll go take a look exactly where it actually, I don't need to guess. So let me go find out where exactly they start for this chip. So special function registers are listed here. These are special function registers and they start from this F80 port A. Remember, we already had port A. Those are special registers that mean they configure the computer in a certain way, the chip in a certain way. So a special function register's job is to allow you to tell which pin does what, the processor what the processor does and how it does it. And then ends in FFFF. You see that? That's where physically it's located. All right. So now we know about a special function register. So a special function register are the one who tell us how this processor is going to operate for us because it is capable of doing many things, many different ways, okay? The only pins that are single function pins, the only pins on the processor that are single function pins are pin 5, and pin 14. Pin 5 is ground, put it to 0, and we usually put this one to 5 volts to make it operate. By the way, it can also operate down to like 1.5 volts if you wanted to operate it down there. They have a version. Why would it be useful to have a processor that only power supply is 1.5 volts? What is so magical about 1.5 volts?
I have a question
about
the layout here. I remember the ICs we used last quarter.
Yeah.
I guess it would be VCC, not VSS. Never mind.
Right.
I see what I'm looking at.
And then if you get into this a little deeper, I hear what you're saying. So typically these are depending on the technology they use. This one is a complementary MOS technology, and for this one, D stands for drain, S stands for source. For us, doesn't mean anything because we are not really digging into the transistors, but that's usually where the ground goes. In the case of the other technology, used to be VCC and VEE, which is for a different technology. That technology is called TTL. But again, it's outside the scope of our conversation. If you want to talk about it, we can chat after class or during the office hours. Okay.
Okay.
Back to our conversation. The reason the voltage difference, this is not important also for our conversation, but I just wanted to throw it in there because if you ever open your let's say your car key, there's a battery in it. That battery is usually a 2-volt battery. It's a disk battery. Or if you open your cell phone, you're probably going to have a lithium-ion battery in there that is 3.7 volts. So these are standard things everybody produces. So if you're going to do a processor that's going to be used in portable devices, small devices, you have to be aware of those limitations of what the batteries can do and things like that. So that's why they do what they do here. All right, we're not going to spend a ton of time. We're not going to spend a ton of time working with the spending on the memory layout. That comes later. We'll spend a lot of time talking about the memory layout. But I just wanted for you guys to kind of know, for the particular chip we are using, they have two kinds of memory. They have a program memory and they have a data memory. Program memory is the stuff you program and it sits there and doesn't change. Data memory is, for example, registers you will change, or where you put your data that your program can change and all that. This is the program memory. Program memory for this chip starts from 0 to 00F. So this is what's built in. So when you have your chip that you're programming and you're using, you've got this. But it can address all the way up to 2 megabyte, but you have to, if you want to use that, you have to add that yourself outside of the chip. Okay, so for this class, we typically not even think about this too much unless it's a quiz or a question or something like that.
Well, if we did want to do that,
I'm sorry?
if we did want to do that,
Yes.
Would you be able to have like an EEPROM for that, or
you would have to probably do a DRAM. I'm sorry, DRAM.
Okay.
DRAM for that. Oh yeah, no, actually I take that back. You could use a EEPROM, or actually you're right. For the program memory, it has to be an EEPROM because it's got to remember it. EEPROM, for folks who don't know, that's an erasable program memory, which is basically what this is. These are non-volatile. In other words, when your power goes out, these data that you put in there don't go away. So that's why we put our program starting at location 0. So we load our program from here down. And don't worry about all the other ratings in here. We'll get back and talk about them later. Now we want to kind of just understand how we can. And then we got this. This gets this once again. I hate to do this, but once again, you'll have plenty of videos on these, and you'll learn more about it. So we in this computer we are given only built-in the data memory only have 256 bytes of memory, so it's not very large. And out of this 256, we have basically allocated 128 byte of it to what we call general purpose register. Okay, so GPR, general purpose register. And from your point of view, when you want these locations starts from location 80 and they'll end at 0xFF. Okay, and your SFR registers are SFR to you, your SFR registers appear right here. So your SFR register, that's the other 128 bytes that start from location F80 to FFF. Now, do you remember what special function registers were, right? We are using those to configure the processor. Fair enough? Awesome. So whenever somebody's talking about SFR, they're talking about this location starting at this location. Whenever they're talking about GPR, they're thinking about starting at that location for us. Now, does this processor always do that? No, there are ways of moving those locations around. There's ways of adding more memory and all that. But for now, we're just trying to learn how do we use the base processor as is. And then later on, we'll figure out how to configure, mess with it, and do all of that kind of good stuff. All right, so let's see where we're going now. Okay, so we got the memories done. We know SFRs are. Okay, now comes the good part. How do we tell this processor to do something for us? So those are called instructions. And the nice thing is there's a nice table starting on page, there's 3 pages of instruction list. And then there are many places we can learn more about this instruction. For the time being, we're going to use this table exclusively for what we are doing. So once again, these are on page, starts on page 3 of what you have in this document, that this PICmicro quick reference guide. And the instructions are listed there. And you look at it, the instructions are grouped into 5 separate groups. Okay, they are grouped into byte-oriented. These byte-oriented operations, these are operations that take a byte, do something to it, and save it into a byte. Okay, so they're called byte-oriented instructions. Then there is another group of, so there's a whole mess of them. You can kind of see them there, right? Then there is a whole other mess of instructions that are called bet-oriented. Guess what? They do what? They take a bet and mess with the bet and save the bet. Are we good so far? Questions?
I'm just taking it all in.
Okay. Yeah. Again, once again, your perception is absolutely right. I'm going over a whole bunch of stuff. I'm basically covering chapter 2 and chapter 3 all one place, just so you guys have a big picture of things. Then as you take the quizzes and doing the homework, you're kind of learning each piece of this as we move forward. All right, so the next instruction set is called the literal operation. These are the operation that literal means constant. So if you want to bring a constant into your operation to add or subtract a constant, multiply by a constant, do that kind of stuff, then use the literal operation. And then the data memory operation we don't use in this class, but they are basically a way of moving blocks of data from one location to the other location. That's all they do. You say, okay, take this chunk of memory from this range, put it in this other range, and that's all they do. We're not going to spend time on those too much. And this is the next important one, control. This is what allows us to do branch, if then else, while loop, and things like that. It's basically a whole bunch of branch on certain conditions, and then go to on a certain condition. Now go to function calls. Function calls are called call, like when you write a function in C and you call it. When you call that function, that's a call function. And then when you're finished, you do a return. And those are instructions that are available in a processor. Okay, so for each instruction in this table, it gives you the description of it, of what it does. It tells you how long does it, this cycle is an instruction cycle. So how long does it take for it to execute that instruction? And this is the machine code. This is how the processor gets this instruction. So if you, let me go way up there. So let's say you do an add WF. You don't know what that is yet. If you do an add WF, the processor will get this values. Now you wonder what D and A are. A for us, for the time being, A is always 1. A is always 1, never changes. And F is the register you selected. Okay? So if you want to write to location 0x80, the F is going to be 10000000, which is a binary 80. Okay. And then this one we'll get back to in a little while, but this basically tells you after you did the instruction, what happened? Did you get a negative number? That would be N, would be a negative number. Did you get a 0? Was the result 0, or was the result created a carry? So those are the 3 let's focus on for now. We'll come back and explain the rest, but it kind of remembers what the instruction results were. So if I added 2 numbers together, did I get a negative number? Did I get a 0? Did I get a carry? But they're useful information. Are we good so far? So this was kind of more of an introduction. I want you guys to have this page open on your computer, because right, as Gavin says, right now was kind of your audience, and we're kind of going through it, and they're all kind of like a movie, so it sounds good and all that. Now we're going to get to actually applying it and see if we really kind of understand. There are lots of issues. The other thing I wanted to share with you is that we also have in the text, there is also a reference document available. And that reference document, I'll go through it manually. Reference document sits on engineeringcs.com, right where all the data sheets in the past have been. And one of the data sheets is PIC 1220 data sheets. You see that? Just like the IC data sheets from last term, from Digital Logic, they also have the same thing. So if you do this, this comes up, and then I'll do a shortcut. So if you do a Control F, you can search for whatever you want in here in this thing. But I know that all the instructions are in chapter 20. So I just kind of, since they use the instruction throughout, and if you just want to know what an instruction does, you don't want to go through all the usage of it. You just want them to tell you what it is. So I usually jump right here first.
Can you have the link to this page?
Yeah, I have the link. The link is in Canvas. Canvas would be the sure way of getting to this always, and it's always there. It's right here, quick reference. And for today, I also put it in the chat. It looked like a lot of people copied and put it in the chat as well. It's all there.
Awesome, thank you.
Sure. So somebody had this one too, which is great. So the 1220, what was I? Well, here. So I'm here. So we talked about the different type of code: byte-oriented, bit-oriented, literal, and control. Those were the different type of instruction. Now let's say, for example, the instruction we were chatting about just a minute ago was add WF. I want to know what add WF does, what are all the ramifications on it. So what I'm going to do is I'm going to jump to this data sheet, and I'm going to say, okay, tell me what add WF does. Oh, I must not have, hang on, let me jump here. Instruction set, I'm in the instruction set. Unless I misspelled it, let me just find out if I misspelled it. ADDWF, okay. So I put in ADDWF and I say, okay, search it for me. Not that one. Okay, this is what I want. So I search till I get to the description. And this is really nice because this is all you ever, more than you wanted to know. in that table I gave you was a summary of it, right? Sometimes you want to know more about it. For example, it says you want to read the full description or whatever. It's maybe a complicated instruction. Add is a pretty simple instruction. So maybe this is a more complicated instruction. But so it says add W is a special register. W is a very special register. We need it quite a bit. So we add W to register F, whatever location they told you to do it. And then if D is 0, remember there was a D in here, you had to put a D in here. If the D is 0, the result is stored in W register, which is in the special register. If D is equal to 1, the result is stored back in F register. So let's do an example just to make sure we understand. So let's say somebody comes in and say, okay, do add, well, actually, let's use what they have here. There's an example they have here. So let's say the W has 17 in it, and whatever the register is has that in it. So if W, if this is what they put in here, the D is equal to 0, the result will be put back in here. But on the other hand, if that thing was set to a 1, the result will be put back in here. Does that make sense? So that's just, so let me put number in here because they use, I'll find it easier if I number it. So let's say somebody comes and said, add WF location 81 and put the result D equal to 1. So what that means is whatever, let's say this location had 25 in it, okay? So if 25 was in there, and let's say W, so this was in that location, and let's say W register had 15 in it, okay? This is add W register, add what is in here with add what's in 81. So I'm going to take this and add it to that, which means the result is going to be 40, right? So where does 40 go? The 40, so after this instruction is completed, then W register still is going to be 15 because D, the second number you give it is a D value. And the D is set to 1, which means the result is going to go to 81, not W register. But if I had come in and instead of putting comma as 1, I would have put comma 0 in here, then this would have remained 25. This would have gone to 40 because with the D equal to 0. Now, in programming, there is a convention which basically says, you see how they describe this. Says if you have these, you see this square bracket, it says you don't have to put D, but if you put a comma and a value, I'm going to assume that value is going to be D. If you don't put anything in there, I'm going to assume the default value. And for here, if you don't put a D value there, the assumption is it's 0. Okay, the default value, well, it doesn't say what the default value is. Add W to F. If D is 0, the result goes there. If it is 1, the result is stored in F. Oh, and default is 1. You see that in parentheses, it says default is equal to 1. So D as a default, if you don't put anything, the value goes into the F register. So I know, so let's go ahead and have you guys put some of this in practice as we go forward. So let's go ahead and take a look at Lab 1.
Real quick, can you highlight where it says that the default is 1?
Sure, let me clean it. I made a mess of this thing, so let me clean it up. Let's zoom in a little bit. and get all lined up. Yeah, the data sheets are data sheets are sometimes worse than my writing. So if you look at it here, see here it says if D is 1, the result is stored back in register F, and then parenthesis default. You see that?
Yes. Okay.
Yeah. And then of course it tells you what the operation is, what the values that different pieces can take, and what the instruction looks like, what is the encoding, which is what is the machine code equivalent of this is. How big it is 1 word, and 1 word is 2 bytes. So yes, the instruction takes 2 bytes, right? 16 bits. So 1 word is 2 bytes or 16 bits. Cycle is how long it takes. We'll talk about what instruction cycle is later on, but that's how long it takes. Some instructions take 1 cycle, some instructions take 2. I think the longest instruction we have takes 3 cycles. All right, guys. Okay. So now let's go ahead and jump into MP Lab and see if we can make sense of what it is that that program is doing, okay? Oh, yeah. So I hate to do this to you guys. We'll talk about it in a minute. So I'm going to go back to the assembly. So there we go. Now, these port A and port B are pretty interesting stuff as well. So let me go back here. Remember, this is the processor. And if I redraw my processors, what it's got, the processor, if you forget, the processor has 18 pin. 2 pins are using for power and ground. We understand that. We're going to do that, no problem. And then the way we're going to use it, we have 8 pins that are going to be what we call RA0 through RA7. And then there is another 8 pin that is going to be called RB0 through RB7. Let's see if anybody can find which pin is RA0.
It's 1, right?
1. Very good. Okay. So the next challenge question, does everybody see that? RA. It's a little bit tricky because it has so many meanings. Now, let's see if we can find RB0.
It's going to be 8.
Yeah. So these are the input and the output ports. So if you want to connect it to something, those are places you do. Now, each pin can be both used as an input and as an output. Okay, so the way it works is whatever is on these pins for RA stuff, so for RA7 through RA0, it's connected to pins, right? We figured out like this is pin 1 and RA7. Someone can help me find it. Anybody see it?
$17 or 16?
16, very good. So these are kind of connected to each other. Now, the way this works is these pins, these values of RA0 appear in this thing called port A. Remember port A was a special register? It's a memory location that we can access, and it's got 8 bits in it. So those pins are directly connected to the values of those registers. Now, I can make him go out, or I can make him go in. You see that? So how do I tell him I want him to go out or I want him to go in? There is another register, which is called tri-state A. And if I put if for the pin 0, if I put for the pin 0, in is 1, so that would be an in. So if I put a 1 in a tris A, which is a register, pin bet 0, then this pin will be an input pin. If I, on the other hand, I put if I put it out here, it's going to be 0. If I put a 0 in it, it's going to be an out. And the way one of the students came up with it, which I still use it because sometimes I forget, is 1 input or 0 input. He said, look, input, it starts with an I, right? I look like a 1. And output starts with an O. O looks like a 0. So if you want the pin to be output, put a 0 in there. If you want the pin to be input. Okay, so Trish A is another general purpose register. It controls whether the things are input or output. And then port A is where the data is stored. So if it's an input, the input goes in there. If it's an output, it takes that value and put it out there. So if you put a 1 in port A location, a 5 volt will show up outside. If you put a 0 in there, 0 volt will show up on the pin. Does that make sense? Any questions? And there is for
I'm looking for a tris A on the register map.
Oh, yeah, let's go do that. Let's go do that. That sounds like a fun thing to do. Somewhere in here. Where is it? I lost my, oh, there it is. So we'll go here.
Oh, I found it. It's
Where is
page
it? So you can help us.
Page 6, very right column, right in the middle.
Right size, middle, right there, right? Very good. Tris A and Tris B. For everything I said about A, there is a B version too. So you get 16 pins that you can mess with, okay? Any questions? All right.
Actually, I do have a quick question.
Sure.
So you're saying, 1 is input, 0 output. Looking at Lab 1, I'm seeing that
yeah, let me go there and so we can look at it together, okay?
Okay.
All right.
I'm just trying to kind of follow along in here. So it says, we'll just go with move WF tris B. So it shows in the instruction that it's setting it as an output, but I don't see anywhere where you're putting like 0 or 1.
We haven't. Let's walk through it. That's great. So let's walk through this real quick. So some of these are pretty self-explanatory. Some of them we have to kind of spend time thinking about. So let's do that together. So if okay. So this one, clear F, what do you think clear, called it CLRF? What do you think it does? You say, if you don't know what it does, you say, let's go find out. So you basically go back to your date sheet, which you have in front of you. You look it up and you say, oh, it clears the F register. You see that? So what does this do? It clears port A. This is just it. When you program, you don't know who came before you, so you don't know if they did good housekeeping and cleaned after themselves or not. So it's always a good idea to, not absolutely necessary, but a good practice to clear A and B. What does it mean to clear it? It means to put 0 throughout. So when you're finished and you look at port A, you're going to have all zeros in there. Okay? Any questions? Anyone? So we do that for A and B, nothing exciting. Remember, we talked about this one, all I'm going to tell you, you have to do this every time. So what are you doing? You doing move LW. So now I want you guys to go back and look to see what move LW does.
Moves the file into the W register, or is there
Not, yeah, F, move F. F is a register, not a file, right?
yes.
So it moves the value 7F. What is the 7F? 7F value is 1, 1, 1, 1, 1, 1, 1. It moves it into W register. It moves it into a W register. What is a W register? It's one of the special function registers like port A, port B. That's all it did. And then it moved WF. What does move WF does? Move WF takes whatever is in W register and moves it into this other register called addCon. Why do we do all this crazy stuff? Remember, this chip can do many things, right? You can have the chip pins be an analog input, analog output, digital input, digital output. And this two instructions, basically, they put a value of 7F in addCon 1, which makes all the pins digital output. We want everything to be digital output. Okay. Now, why couldn't I take a 7F and put it directly in addCon? Because the people who designed this chip didn't give you the path, didn't put the wires in to put in because it's too expensive. They only allow you to pull things and put it in W register. Then when you're in W register, then you can put it anywhere you want. So you will find out that everything almost has to go to W register before it can go anywhere else. And then, okay, now let's go ahead and see. Now that you know that, let me ask you one question. And I would like you guys to all respond maybe in a chat or whatever way. Chat would be probably the easiest way, just to me directly, so you don't influence other people.
I see.
Tell me what happens here when you execute these two instructions. What happens? And I'll give you a hint. Whatever happens to port B, which is a register, right? I'm sorry, Trish B. Oh, somebody's way ahead of me. Okay, good, good, Vlad. But what value goes into Trish B? Let's start with the value. Very good, very awesome, awesome. So Trish B, all the pins are set to 0, which means what? Which means port B, whatever you write into port B, whatever is in port B is going to end up on the corresponding pins, right? And it's going to be an output going out of the processor. All right, now tell me what happens here and with this two instruction. So this one messes with Tris A.
So the W register, that's going to be constantly changing to whatever value you need at that time. That's kind of
that is like a hub and spoke, you know, you have like a train station where everybody's got to come in and come out of the same spot. If you want to go someplace, you got to go to the central station before you get to go someplace else. If you want to move things from place to place, a lot of the time you're forced to go to W register because they're not connected to each other. Yeah, so yeah, W register changes all the time.
Okay, so you're constantly just giving it new values and using it, pulling from that to do other functions. Okay, that makes a lot of sense.
Yeah, so W register is a working, the real name is working register. And some processor call it an accumulator. So like if you're using Intel product, they call it A register. Just different name, same functionality. And then, so you move it between them. Any questions so far? So what did we do? So we all know that now Trish A has all zeros, right? Except for the least significant bit is 1. What does that mean?
That means it's now an input. All the pins on RA are input.
Only 1. Only pin.
Oh, 0.
0 is input, right? And if you remember when you were doing stimulize, when you did this code in lab 1, what did you do? You took RA0 and you kept changing it because that's the only input. And it was kind of looking at the inputs. So what you really did was you did your chip. I'm going to erase it real quick. You basically, all you did from here to here, you got your chip. You said, okay, RA0 is going to be an input and RB0 through RB7 is going to be an output. You see that? That's all you did. So that's all we've done so far. And you say all of them are digital. We're not getting any analog input. We're not putting any analog output. We're making everything digital. So now come the real work. I know we're almost close to 11 o'clock, but I want to kind of carry this forward. Hopefully you guys can hang around for a little bit longer. So what does this do? This basically, okay, so there are other instructions available. And then it moved 0 to count, right? To create a variable called count and moved it to count. And then we create and cleared another register called last in. And then look at what it does. It moves FF. Now it takes whatever is in port, whatever is in port A, puts it in the input. You see that? Whatever is, and then whatever is input moves it to W register. And once again, if you want to know how that works, you go back to the summary sheet. If you need more information, then you go to the data sheet to figure out what it does. So in this case, it basically took whatever is in port A. What was port A? Port A was the input, remember? Pin 0 was the input. Put it in the input, put it in a variable so we can mess with it. And then took this, because if you want to work with this, you have then the next instruction took whatever was in here, put it in W register. Then exclusive OR last in, what does that do? So if I have two values, last in value, if I exclusive OR this with the input, when do I get 0? Can you think about when you're going to get a 0? Under what condition an exclusive OR of, because this what it's doing is basically exclusive OR in W register, which has the input in it, with the last value, which is another register. So if I exclusive OR to register, what's going to happen?
They have to have different values to get one.
If I have a different value, what do I get? Do I get a 0 or a non-zero?
You get a non-zero, right?
Right. What is the only condition I'm going to get a 0?
When they're both 1?
They're both equal. Not necessarily 1.
Yeah, I guess it's true. Yeah, it could be 0, yeah.
So what does that mean? What does that mean? That means nothing changed. If I get a 0, out of here, that means nothing changed. Does that make sense? And LW with 0, 1. Then it says, okay, and then it makes whatever the input was, the last in, it moves that one in there. And then it tests. This gets kind of weird, but I'm going to jump around a little bit on this one. This is a call increment, and all that is a little piece of code, and all it does is increments the count. It's nothing exciting. I'll show you. And this was just to show you how function works. Simple function works. Let me clear everything. So if you go over here and you see include, that's the function, that's the start of a function. And the way you call it and give it, this is called the label. You give it the label name. So it jumps from here to here, moves count to to W register, adds 1 to it, because there is no instruction to add 1 to count directly. So you have to take the count into W register, increment it, and then move it back to count. And then since port B is the output and we are counting how many pulses we're getting, moves that to port B and returns. So let me stop right here. So what we've done today is kind of introduce you to a bunch of new things. How input and output works on a chip, where can you get a summary of the instructions. If you want to learn more about what that particular instruction does, where do you go to learn about that particular instruction and things of that nature. So these are the bases. So at this point, my hope is at this point you can sit down and figure out how Lab1 works, okay? Between now and the next time we get together on Wednesday, you may want to also, everything we've talked about is kind of getting you also ready for Lab2. So you might want to review Lab2 because Lab3 goes through everything I talked about, the IO stuff, the input and output in the lab. And then it says, build a device you write a program for your processor that takes a 4-bit number, adds it to 4-bit number, and displays it. Okay? Very similar to Lab1. Very similar to Lab1, except instead of having 1 input, you've got 4 inputs. Okay? And it really forces you to where you're getting those 4 inputs. It doesn't give you an optional. It says you're gonna get the operand 1. It calls it operand 1. The first operand, you're gonna get it from bit 0 to 3 of port B. The second operand, you're gonna get it from bit 4 to 7, and your output will come out of port A. See that? Okay, so you write a program that accepts 2 inputs and generate the sum as an output coming out. And my recommendation to you would be start by doing the pseudocode. The first part of the process is pseudocode, which is a high level thing. So, okay, when I want to design this thing, what are the things I got to do? Well, I got to do some initializations, right? Some initialization has to happen. You can be more specific, or you can, for now, leave it at that level. Then what do I have to do? Well, I have to be able to get operand 1, right? You got to get it into the register, put it in a nice place where you can actually do an add to it, because the real work is just add, right? And then you got to get operand 2, whatever you need to do that. And then you need to add operand 1 and 2. And then the next step might be display result. And maybe another would be wait for input to change before doing the next sum. Because you don't want to keep, if the user didn't change the input, you don't want to sit there and keep adding numbers, right? You want to wait for them to change the number. So if between now and Wednesday, if you could go over Lab1 and make sure you are kind of solid on Lab1 and you understand what is happening there, then take a crack at least doing the pseudocode for Lab2. Then maybe next week we can start learning more about programming and the instruction by doing Lab2. Does that make sense? Any questions for me before we call it good? And if you want to go back and see this one, I will try to record it and make it available or save it. And if it's decent, I'll just put it on the YouTube and put a link in the Canvas, or maybe mail you the link. Okay, so let's see. I have a question about Lab1 grading. Sure. Yeah, so go ahead. So we're done. I'm not going to go through anything more new here. So now I'm going to open it up to questions. I see Vlad has a question about the grading. So ask me that question, Vlad, or do you want to? Okay, he's talking to someone.
So yeah, I got a question about so in the lab, you want us to show the stimulus window
Mhm.
and the simulator output. What exactly?
Let me bring it up. I was going to use some from someone's lab, but I think I'll just bring it up and show you. So the components that when you write a lab, when you write these labs for this course, there are a few things you always have to include. You do not need to include the assembly code. That's the first thing, because it's redundant. Because what do you need to include? You need to include this. This is called a disassembly code. Because if you include that, the assembly is already there, so you're including it's redundant. And you need to copy and paste it. Don't put the window in there, because window only going to show you a little piece of it. You can literally say edit, select all, edit, copy or control C and control V it into your document, okay? So that's the first thing. What's the next thing? The next thing is the stimuli window. Just use a snippet tool or whatever the equivalent is on Mac and just snippet this piece. Let me actually do it so you can see it and paste it into the documents. Snipping tool. So you just grab this thing and just save it into your document. Okay, so that's the second thing. Are we good so far? And then the third thing. So the third thing you want to do, is every bit as important as snippet this one. After you've done a little running, so there's numbers here, okay? So it shows that you're running it. Now, you only have to do it once. Don't put 50 of these things if you have 50 options, right? Just once. I just want to know that you've configured it, you're looking at the right variables and all that. And I want to know your stimuli is set up correctly, so you're actually giving it the right input. I do not need to see all the possible inputs. So then you say, how do you know I tested it correctly? The way I know I tested it correctly is you're going to give me a test plan. You're going to say, I tried to give it this input, this is the output I expected, and this is the output I actually got. So think about a table with 3 columns. And the first column is what you're going to give it as an input. Second column is what you expect as an output. And the third column is what did you actually get, and life was good, right? If it's different than what you expected, then you got to explain. My guess is at that point, the reason you're doing the lab is you figured out how it works, and your expectation and what comes out is the same. And then finally, the first item you need to include is a pseudocode. Now in Lab 1, that was not necessary because the code was given to you. You didn't have to write. Pseudocode is kind of a high-level design for your code. If you jump in and try to write the code without having a bigger picture of how the pieces of the code going to fit together, you'll get lost very quickly. So this is an idea where you use just regular English or C-level syntax, doesn't have to be precise. And you say, okay, so the pseudocode would be, for example, for Lab 2, we just went through, the pseudocode would be get operand 1, get operand 2, add them together, display it, wait for the input to change. Those are the big 5 steps. And now you can actually focus on implementing each one, which makes it for a much easier problem to solve. Okay.
Also, is the pseudocode necessary, like 100% to be included in the labs? Say like
yes. I want to see that you thought through it and you want to see it in the same sequence. I have to tell you that I catch myself, and I have caught other experienced programmer trying to avoid doing a high-level design before they do the code. And they invariably take longer and maybe not even solve the problem the way it was intended to be solved. So high-level design is really, really important. It's so important that if you go to an organization and look at the most senior engineers or programmers in the group, you'll find that the most senior programmers are responsible for high-level design, and the most junior are responsible for actually doing the coding. Okay, because the coding is like digging ditches for computer science, right? Coding is the lowest level of competence. The highest level of competence is figuring out what the problem is and breaking the problem to its big steps that other people can focus on getting it done. So, and also it speeds up our process. You will finish the code faster if you do a pseudocode and start there instead of that. Thank you for giving me a platform to get on my soapbox on this one. Let's see.